So in this video, I will be presenting the solutions of review problems for basic principles, concepts, and definition in thermodynamics. So this is in the first chapter of every thermodynamic books. Okay, these types of problems. So let's go ahead with our problem number 1. So what is the mass in grams and the weight in dynes and in gram force of a 12 ounce of salt? So the given here, which is 12 ounce of salt, the given is actually already the mass, no? So that is just the mass, 12 ounce. So we want to convert this mass, 12 ounce, to grams. So we are given an initial conversion here as part of the problem. 1 pound mass is equal to 16 ounce. So let's go ahead and multiply that. 1 pound per 16 ounce. Okay? And then we know that 1 pound or 2.205 pounds is equal to 1 kilogram. And 1 kilogram is equal to 1,000 grams. So if I cancel my units here by means of multiplication, ounce cancels out, pound mass cancels out, kilogram cancels out, and we have the final unit, which is in grams. So let's go ahead and get our calculator and input the given. So we have 12 times 1,000 and then divided by 16 times 2.205. So the answer is 340.14. Let's write that in 340.14 grams. So that is the mass in grams. Okay? Next, what is the weight in dynes? So for the weight, we will simply use the formula mass times G over K. Okay? So the mass that we already have is the 340.14 grams. And if we are to get the weight in dynes, then the gravitational acceleration, which is 9.65 meter per second square, should be converted to centimeter per second square. So we will simply multiply 100 centimeters per 1 meter. Okay? And the K that we will use here, because this will be in grams per centimeter, is simply 1 gram meter over dynes second square. Okay? So let's cancel. I'll show you the cancellation of units. Grams cancels out. Meter cancels out here. This should be in centimeter. Okay? Gram, centimeter per second square. Centimeter cancels out. Second square also cancels out. And the final unit is in dynes. So what is the weight? Let's go ahead and input that in our calculator. So we have 340.14 times 9.65 times 100, then divided by 1. So that is 328,235. So I'll write that down here as my answer. 328,235.10. Okay? Dynes. Okay? Next, what is the weight in gram force? Okay? So for the weight in gram force, we already have the mass again. So we will use the formula mg over k. So the mass is 340.14 grams. And 9.65 times 100 is very easy. That's 965 centimeter per second square. Now here, because we want to solve the weight in gram force, okay, we will use 980.66 gram mass centimeter over gram force second square. Okay, So gram mass here cancels out, centimeter per second square cancels out here, and the final unit is in gram force. So the answer, weight is equal to, so we have 340.14 times 965. Then let's divide it by 980.66. So the answer is 334.71. 334.71 gram force. Okay, so that is our final answer. So let's go ahead to our second problem. Problem number 2, we have a mass of 0.1 slug in space is subjected to an external vertical force of 4 pounds. Okay, and so let's go ahead and write the given. So we have mass is equal to 0.10 slug, and then we have a force which is equal to 4 pounds. Okay, if the local gravity acceleration is equal to 30.5 feet per second square, so we have g is equal to 30.5 feet per second square. And if friction effects are neglected, determine the acceleration of the mass if the external vertical force, so this one, the external vertical force is letter A acting upward and letter B acting downward. So let's first consider letter A, acting upward. So we have here our mass. To illustrate, this is our mass, and our mass will have a weight, of course. And that weight is equal to mg over k. Now, if our force, external vertical force, is upward, let's say that is F, then therefore, the F net, the net force, will be equal to the weight minus the upward vertical force, which is 4 pounds. Okay, so let's go ahead first and solve. What is the weight? What is the weight of our mass? So I have mass is equal to 0.10 slug, 0.10 slug, okay, times g, 30.5 feet per second square. K here would simply be 1. Okay, 1 slug feet over pound force second square. So we can do the cancellation. Okay, and the unit here would be, of course, in pound force. So the answer to that is, so the weight of our mass is equal to, so that is 0.10 times 30.5. So I will get 3.05 actually. 3.05 pound force. Okay, so I have here my force. F net would be equal now to F minus W. Okay, so F net is equal to 4 pounds minus 3.05 pounds, and that is equal to 4 minus 3.05, 0.95. 0.95 pound force. But we want to solve the acceleration. Okay, we want to solve the acceleration of the mass. So we apply the law of acceleration, Newton's law of acceleration, and we know that that is F is equal to ma. Okay, we can still use the k. Okay, so A, from this equation, A is equal to F times k over m. So our F here is the F net. Okay, do not forget. F net is 0.95 pound force times k. Okay, k is determined by our mass and our units, no, in general. So our mass is equal to 1 slug, or 0.1 slug, 0.1 slug. Okay, so the K here would simply be 1 again. 1 slug feet over pound force second square. Okay, so pound force cancels out, slug cancels out, and the final unit is the acceleration in feet per second square. So that is equal to, okay, 0.95 divided by 0.10. So we have 0.95 already, and let's divide that by 0.10, 0.1. So the answer is 9.5 feet per second square. 9.5 feet per second square. Now that is letter A. If the external force is acting upward, okay? The external force is acting upward. What if the force is acting downward? So that's letter B. Downward. So if this is my mass, okay, it has a weight, which we have already solved, and our weight is equal to 3.05 pounds. Okay, if the external force F, which is 4 pounds, is acting downward, then our F net would now be equal to 4 pounds plus 3.05. Okay, that's our total force. So we have 7.05 pound force. So we will still use the same formula that we have derived right here. A acceleration is equal to our F net times K all over M. Not A, but all over M. So we have 7.05 pound force. Again, K would be 1 slug, okay, feet per pound force second square, and our mass is equal to 0.1. So slug cancels out, pound force cancels out, and again we have feet per second as our unit. So A is equal to 7.05 divided by 0.1. So that is actually 70.5. 70.5. So that is the answer. 70.5 feet per second square. That is if the force 4 pounds is acting downward. Okay? Let's go to our third problem. So third problem, we have the mass of a given airplane at sea level where G is equal to 32.1. G is equal to 32.1 feet per second square is 10 tons. So our mass is equal to 10 tons. So that's the mass of the airplane. And at sea level, the local gravitational acceleration is 32.1 feet per second square. Find its mass in pounds. So similar to our previous problem, mass in pounds, slugs, and in kilogram. So that's the first part. And its gravitational weight in pounds when it is traveling at 50,000 feet elevation. So the acceleration of gravity decreases by 3.33 times 10 to the 6 for each point of for each foot of elevation. So let's answer here first. What is the mass in pounds, slugs, and in kilograms? Since this is already the mass, 10 tons, okay, we simply have to convert tons to pound mass. And 1 ton is equal to 2,000 pounds. Okay? So that's very easy. You cancel ton. And 2 times 2,000 times 10 is simply 20,000. So 20,000 pound mass. Okay? So that is the mass in pounds. How about the mass in slug? So for the mass in slug, we will use the conversion. 20,000 pounds. The conversion is for every 1 slug, we have 32.174 pound mass. Okay? So let's go and get our calculator. So we have 20,000 divided by 32.174. And we have 621.62. 621.62. So this one is cancel pound mass, and the unit is in slugs. Okay? So we're done with that. Next is in kilograms. So we know the conversion of pounds to kilograms, so we'll simply use that. So again, we have 20,000 pound mass times, for this one, we have 1 kilogram is equal to 2.205 pounds. Okay? So calculator, we have 20,000 divided by 2.205. The answer is 9,070.29. Okay, let's write that down. 9,070.29. So it cancels out. Final unit is in kilograms. Okay? So last in our problems, let's cross that out, is the gravitational weight. Okay, the gravitational weight in pounds when the aircraft is traveling at 50,000 foot elevation. So what we want to find out here is what is the G, or what is the gravitational acceleration at 50,000 feet. So we have here the decrease in gravity is 3.33 times 10 to the negative 6 for each foot of elevation. So therefore, the gravitational acceleration at 50,000 feet is equal to, first we have the gravity at sea level, then we subtract the decrease per foot of gravity, which is equal to 3.33 times 10 to the negative 6, and multiply that by the height. Okay? So the G at sea level is simply 32.1, that's the given, feet per second square, minus 3.33 times 10 to the negative 6. Okay? So this is feet per second square per feet. Okay? So we multiply it by 50,000. Okay, we can see that we can cancel out feet. Okay, so we are just subtracting feet per second square. 2 units are in feet per second square. So let's go ahead and get our calculator. So we have 32.1 minus 3.33 exponent negative 6 times 50,000. Okay, I made a mistake here. So let me write that again. So we have 3.33. No, that's not the one. So again, we have 32.1 minus 3.33. So this should be the bottom, and then negative 6, okay, times 50,000. So G is equal to 31.935. 31.9335 feet per second square. So this is the G at 50,000 feet. Okay? So if we will solve for the weight of the aircraft while traveling at 50,000 feet, we now have W is equal to mg. This is weight at 50,000 feet, so mass does not change. Okay, mass does not change, and the mass in pounds is 20,000. So 20,000 pound mass. Actually, it's better if we will use the mass in slugs. So let me go ahead and erase this one. Okay, so that we will just use K as 1. Okay, so 621.62. 621.62 slug times G, 31.9335 feet per second square. So RK, so this is over K. RK is simply 1 slug feet over pound force second square. Okay? So feet per second square cancels out, slug cancels out, and the final unit is in pound force. So weight is equal to, so we have 31.935, multiply that by 621.62. So the answer is 19,850.50 pound force. 19,850.50 pound force. So that is our weight in pound force. Okay, weight in pound force. So let's go ahead with our problem number 4. Problem number 4, we have a lunar excursion model or a lunar excursion module weighs 1,500 kilogram force on Earth. So these are very important details that this is on Earth, where G is equal to 9.75 meters per second square. What will be its weight on the surface of the moon, where G is equal to, the gravitational acceleration of the moon is 1.70 meters per second square. Second question, on the surface of the moon, what will be the force in kilograms? What will be the force in kilogram force and in Newton required to accelerate the module at 10 meters per second square? So first, to solve for the weight on the moon, we must realize, from the previous problem, that mass does not change. Okay, mass is constant. So whatever is the mass on the Earth is also the mass on the moon. So the weight on the moon would be equal to the mass times the gravitational acceleration at the moon. So we already have the gravitational acceleration of the moon. What we want to find out is the mass of the lunar excursion module. So we have the weight of the LEM. The weight in the Earth of the LEM is equal to 1,500 kilogram force, where G is equal to 9.75 meters per second square. Okay, so if we have weight on the Earth is equal to mg over k, the mass is equal to the weight on the Earth times K over G in here in Earth. Okay, so the weight in Earth is equal to 1,500 kilogram force times K. So before we determine K, what is RG? RG is 9.75 meters per second square. So the correct K is equal to 9.8066 kilogram mass meters per kilogram force second square. Let's cancel some units. So kilogram force cancels out, meter per second square cancels out, and the final unit is in kilogram mass. So the mass of our LEM is equal to, let's get our calculator. We have 1,500 times 9.8066 divided by 9.75. So the answer is 1,508.71. 1,508.71 kilogram mass. This same mass will be the mass of our LEM at the moon. So we go ahead with this equation. Okay. The weight of our LEM on the moon is equal to mass. So mass is 1,508.71 kilogram mass times G, which is 1.70 meter per second square. Okay, we will divide it by K again. And K is equal to 9.8066 kilogram mass meter over kilogram force second square. So meter per second square cancels out, kilogram mass cancels out, and the final unit is in kilogram force. So weight on the moon is equal to 1,508. We already have that. So just go ahead and multiply 1.7 and divide 9.8066. So the answer is 261.54. So that is the weight of the LEM, or the lunar excursion module, on the surface of the moon in kilogram force. Okay, so next question is, what would be the equivalent of this kilogram force in Newton? So this is already our answer there. And for that, we have to apply a conversion. Okay, so we already answered this one. What will be the weight on the surface of the moon in kilogram force? So this is supposed to be in the next question, the highlight. On the surface of the moon, what will be the force in kilogram force and in newtons required to accelerate the module at 10 meters per second square? So we will now again apply the third law of motion. F is equal to ma over k. K is the proportionality constant, so that the units will all be cancelled. Okay, so we have the mass of the lunar excursion model, 1,508.71 kilogram mass, and we want to accelerate it at 10 meters per second. So we simply multiply 10 meters per second square. Okay, so the K there, in order to get kilogram force, which is the required unit here, is again 9.8066. So kilogram mass meter over kilogram force second square. Okay, so meter per second square cancels out, kilogram mass cancels out, final unit is kilogram force. So F will now be equal to, so we have 1,508 0.71 times 10, then divided by 9.8066. So the answer is 1,538. 1,538.46 kilogram force. Let me highlight that. And then finally, we have to convert the kilogram force, the force in kilograms, in newtons. Okay, so to do that, we will simply have the conversion. We will have the conversion from two k's, no? All k's are equal, okay? First, we have 9.8066 kilogram mass meter per kilogram force second square. And another k that we use in the metric system is 1 kilogram mass meter per newton second square. So what do we see here? My kilogram mass cancels out. Meter per second square cancels out. So I will now have 9.8066 newtons is equal to 1 kilogram force. Okay? So if I have 1,538.46 kilogram force, so to convert to newtons, I would simply multiply 9.8066 newtons per kilogram force. Okay? That one cancels out. So we will have our answer multiplied by 9.8066. And the answer is 15,087.1. So 15,087.1 newtons. So that is the answer. That's the answer in newtons. Okay?